So I just wanted to quickly continue the conversation that we began today in class about phosphorylation. And so you will remember that we broke down phosphorylation into two distinct categories for the process of cellular respiration. It was substrate level phosphorylation as well as oxidative phosphorylation. And so oxidative phosphorylation involves the indirect production of ATP as a result of a bunch of redox reactions. And so I want to spend a little bit more time discussing the electron carriers, coenzymes NAD+ and FAD, and how their structure affects their function in their role as electron carriers. And so before we start talking about NAD+, there are some important concepts related to chemistry from grades 9 and 10 that I think will be helpful in understanding what's going on. So here I have the standard atomic notation for hydrogen. And in fact, NAD+, how it's going to function as an electron carrier is to remove hydrogen from glucose. So that's why we're discussing hydrogen. So given this atomic notation, I have the mass number and I have the atomic number here. So this one down here tells me that every neutral hydrogen atom is going to have a single proton in the nucleus and a single electron and 0 neutrons, right? So really what that means is that if I take a neutral hydrogen atom and I remove an electron from it, so I get rid of this guy, now it does become a hydrogen ion H+. However, another term that is often used to refer to it as is simply a proton, because once that electron is removed, the only thing remaining is that single proton in the nucleus. So I'm not going to write out the whole word proton, but really that's really what I'm saying. Yes, I'm going to go write it. Here we go. So that's what you need to understand before we move on. So NAD+ is going to remove 2 hydrogen atoms and kind of use some of the parts. Where is it getting the hydrogen atoms from? Our glucose molecule, our fuel molecule that we're breaking down because of the immense amount of potential energy stored in its bonds. So in removing those 2 hydrogen atoms, we're going to have basically double what we saw in this Bohr-Rutherford diagram to begin with. We're going to have 2 protons and 2 electrons. So what happens to them? Well, NAD+ ends up grabbing 1 of the protons and 2 of the electrons, and that inevitably ends up producing a molecule of NADH, and that's just the reduced form, okay, of NAD+. So we've reduced the charge on NAD+ by adding in the proton and 2 electrons. Let's look at this in a little bit more depth. And so a question that I often get asked is, why is it that only 1 of the protons is getting added on, but we need 2 electrons? So let me dissect that a little bit for you. So if I'm adding a neutral hydrogen atom onto NAD+, then I'm going to need 1 electron and 1 proton. So if I'm adding a single H atom, I need 1 proton and 1 electron. But the reality is that here I have this positive charge on NAD+, which means that I also need, I'm going to need an extra electron, 1 more electron than can be donated by a single hydrogen atom. So that's why I need only 1 proton and 1 electron to make up the H atom, but an extra electron added in to neutralize the charge, because NADH is of course a neutral molecule. Now what that leaves is a single proton, and that we're using the H+ symbol to describe, as I just spoke about. So that's a difficult concept to understand, and if you need me to break that down in class tomorrow, I am more than happy to do that. And so that plays out in terms of the molecular structure of NAD+ versus NADH. And if you take a moment to inspect to see the differences between them, I think that the differences between them become fairly obvious. But this is a big molecule, so you might have to do a little bit of looking first. I'm going to help you out here. So you'll see that here is the hydrogen. Remember, we're adding only 1 hydrogen onto NAD+ to make NADH. So really, NADH should only have 1 extra hydrogen in comparison to NAD+. And so here is where it gets added on. Right? And you can see that right here. and also the extra electrons that get added in. Well, take a look over here. You'll see the positive charge here, and then no positive charge there. But what's not written, and you may remember this from Lewis structures in grade 9, or grade 11 rather, is that even though we don't write them into the structure, there are some understood non-bonding pairs that are actually there, right? So nitrogen right now is not stable. It's not happy because it only has 1, 2, 3, 4, 5, 6 electrons. So even though they're not written, there are like 2 little electrons right up top there. And so that accounts for some of the structural differences and the addition of the electrons. Now, lucky for you, you don't have to really know that, but for those of you that are kind of curious about what the differences are, there they are. So another question that often gets asked is, well, what happens to this H+ ion? Like, what happens to that? Well, there are lots of uses for molecules. Molecules consistently get recycled within a living organism, living thing. So this just gets kind of absorbed into the cytoplasm and is going to be utilized for some other function somewhere else in the cell. So in this process, what's important to know? Well, what is NAD+ actually doing here? Well, it's grabbing onto electrons, right? Its role is as an electron carrier. And so in grabbing onto those electrons, later on, it's going to rid itself of those electrons, and that's going to, at the most opportune time, it's going to release a whole lot of energy, and we're going to use that to produce some ATP. So FAD is just another electron carrier. It's just a different one. And so they both have the same function, just they kind of come in at different points in time. So again, it's just an electron carrier. It's going to grab some hydrogen atoms from glucose again and form FADH2. So even though we can't really see the charges being affected here, there is a shift in the relative charge next to certain atoms within the molecular structure. Another way also in organic chemistry we often refer to reduction as not only a reduction in charge but an increase in the hydrogen content, if that's helpful for you to remember. So really we're taking FAD plus the 2 H atoms and plunking them right on an FAD molecule. The FAD molecule is quite a bit larger than this, but this is a nice simple diagram that would serve our purposes. Just know that the R groups here represent the rest of the molecule where there isn't really any change in the structure. So looking closely, we can see that this nitrogen ends up having one of the hydrogens attached to it, that's here, and then this nitrogen over here ends up having the hydrogen attached. And of course there are those electrons that we don't see in the structure but are understood to be there based on us following the octet rule. Okay, so during the process, just to sum things up, during the process of cellular respiration in some of the earlier stages like glycolysis and the Krebs cycle or the citric acid cycle, during those phases, that's where we're making these electron carriers. We're taking NAD plus and making NADH, taking FAD and making FADH2, and so they get made in the early stages where they end up traveling to later stages, and that's where we see the big payoff of ATP during oxidative phosphorylation. Think of it sort of like, you know, investing money in some kind of a stock or a bond or mutual fund, whatever, right? So you invest a little bit at a time, and at the end, you hope that there's going to be a big, big payoff, right? So the energy that's going to be gained by these reductions is going to be liberated in the last stage of cellular respiration, which is the electron transport chain and chemiosmosis. That's where the big ATP payoff is going to happen. So this is a lot for you to take in right now. We'll be able to go back later on and take a look at some of this and put the pieces together. So if you need to ask for clarification for tomorrow on some of these concepts, I'm happy to oblige. So get your questions ready.